Welcome to this web lecture on the drop heuristic, which is a heuristic that we can use for the network design problem. In a previous web lecture, we looked at the network design problem and the mathematical formulation using the example of transporting water, not as historically done on aqueducts, but using pipes as we do these days. So Brabant Water is a company that ensures that all households in the province have a steady supply of fresh drinking water and also ensure that the wastewater leaves the house and is being treated before released into the environment. Brabant Water uses a network of pipes as a backbone, which consists of a freshwater spring, sewage water treatment plants, and of course in between the cities that are somehow being connected using these pipes. So for this problem, we would now like to find a good solution. Not the best solution, but a good solution. And if we want to do this, we usually use heuristics. A heuristic is a well-defined intelligent procedure designed to find an approximate solution to an optimization problem. So in short, a heuristic is an algorithm that finds a solution, but the solution may not be optimal. So an algorithm is a systematic procedure that in a finite number of steps produces the answer to a question or the solution to a problem. So also our heuristic has to be problem-based, has to give us an unambiguous set of instructions, and it has to terminate. The reason why we're using heuristics is that they're faster than exact methods, that optimality may not be necessary in a given case. I would argue that that is the reason that we usually do not use heuristics in network design, because of course we have these strategic, very long-term decisions where optimality is actually great. But then on the other hand, heuristics, and in particular the drop heuristic, results in easier to understand solutions. Some other heuristics result in solutions where you really can't interpret, but the drop heuristic is very good at coming up with solutions that you can quite easily explain to practitioners. So let's look into the drop heuristic. In the first step, we initialize a set A hat with all arcs that we currently have in the graph. So for example, if there is no way that we can build a direct pipe from Den Bosch to Tilburg, then we don't have that in the set in the beginning, but every arc that we could potentially build, we throw in. Then we start iterating. And for each arc in this set A hat, we determine if dropping this arc results in a feasible solution. If this is feasible, then we calculate how much our costs reduce if we drop this arc. So we're calculating lambda, capital lambda. And now, if nothing exists where we have a capital lambda of greater than 0, so a positive capital lambda, then we terminate, because then we definitely found the best solution this algorithm can provide us with. Otherwise, we drop the arc ij, which maximizes lambda ij, and continue from step 2 without this arc, and then we iterate until we eventually terminate. So let's look into an example. We have this example with just a source and a sink and 2 intermediate nodes. And of course, each of these nodes, each of these arcs has fixed costs, has variable costs, and has a capacity associated. And in this case, the first thing is a variable cost, the second one is fixed cost, and the last thing that we denote on these arcs is the capacity. So now let's look at the first step. In a first step, we determine the current costs using the current flow. And the currently best flow is this here. So we send a flow of 1 from S to 1. We send a flow of 2 from S to 2 to 1. And then a flow of 3 from 1 to T. And we can do so using the minimum cost network flow problem. And that tells us, okay, costs are 30 right now. Now we're checking how much we can reduce costs for each of these 5 arcs. So what we're doing is we're throwing the minimum cost network flow problem for each of the setups with 1 arc less into Gurobi. So, for example, if we drop the first arc, we see that we're reducing costs by 1, so we go from 30 to 29, as you see here in this code or in this output of Gurobi. We can do this, of course, for all combinations, so for all arcs. And if we do so, we see that dropping the arc from 2 to t actually reduces our costs the most, and it reduces our costs by 4. So this is the arc that we're now going to drop. Then we end up with this network where the blue arc from 2 to t is no longer feasible. We can determine the current flows and the current costs, and we get a current cost of 26 and actually exactly the same flow. So the only thing we reduced was those fixed costs associated with operating the pipe from 2 to t. Now we continue from here. So we're still figuring out which arc we can drop and how much this reduces our costs. And we figure out that now for the first time that we iterate this algorithm, it is actually possible that something becomes infeasible. And if we particularly look at this arc here from 1 to t, it's fairly obvious why this becomes infeasible. Because if we have a flow of 0 here, because this pipe is not being used, a flow of 0 here, we clearly cannot send a flow of 3 through this network. But we still have one arc that we can feasibly drop, which is from S to 2. And this is exactly what we're going to do. So we're dropping this arc. And this results in a new network, which is currently giving us a cost of 23. And we send all flow from S to 1 to T. Now in the next step, we're looking into what else we can drop. And already if we looked into the minimum cost flow in the previous slide, intuition tells us that we can still drop the arc from 2 to 1. And this is also exactly what we're going to do now. So now we're going to drop this arc and we're going to have a lambda of 1. So we're reducing costs 1 further. So the final network flow that we're seeing here is this one here at current costs of 22. We can obviously try to drop either of the 2 remaining arcs, but I think it's fairly obvious that this won't help us anything, because as soon as we drop any of these 2 arcs, we cannot send a flow of 3 anymore and we become infeasible. There's one special case that makes things a lot easier, where you do not need Gurobi, where you don't have to actually solve the minimum cost network flow problem every single time. And that is this case where we have variable costs of 0. So as soon as all variable costs are 0, the lambda ij actually equals to the fij, so the fixed costs, if we drop this arc and if dropping is feasible. So what we can do is we can just always drop the most expensive arc, which can feasibly be dropped. So the only thing we have to do in the beginning is we have to sort our arcs in the order of fij, and as soon as we reach a certain arc in our operating procedure, we just have to see if we can find any feasible flow. And since we don't have any variable costs, we don't have to think about, is this the cheapest one or is it not? We just have to find any feasible flow where this is being satisfied. What I would like you to do for this very simple network is to determine how the final network looks like if we have a flow of either 2 or a flow of 4 through this network without any variable costs. So what I would like you to take away from this web lecture on the drop heuristic is, first of all, what the drop heuristic is, obviously. Secondly, I would like you to remember that you can integrate Gurobi in methods, and in particular here it makes a lot of sense. What I would like you to also remember is this shortcut. So if there's no variable costs, things get a lot easier. And this is actually also what I would like you to work on. So for these 2 special cases, for the flow of 2 and for a flow of 4 on the previous slide, please come up with the cheapest network design. Thank you very much.